All right, so who is ready for our last section of Unit 6? Yay! Well, I don't know if y'all get excited or not. You have a test now. All right, so we are, regardless, going to go over the last section in Unit 6, which is complex zeros of polynomial functions. And I'm excited to say that for this section, you're going to do the identical thing that you just learned in the last section, okay? We're going to find all the possible zeros and plug them in until we find the actual zeros, okay? So the process is exactly the same. The only difference is you may get complex zeros, okay, which means you may end up with answers that have i's. Now, i's are not going to give us x-intercepts, but we can still get solutions for x, right, that have i's in them, whether we graph them or not. So something to be aware of whenever we're looking at complex zeros is that they show up in conjugate pairs. Okay, so what that means is that if a plus bi is a complex zero of the polynomial function, then a minus bi is also a zero of the function. Okay, so what that tells us is that they show up in conjugate pairs. So if a plus bi is a zero, then a minus bi is a zero. Okay, so for example, if we have 2i is a zero, then we should also have negative 2i. Okay, or if we have 4 minus 7i is a zero of our polynomial function, then that means that 4 plus 7i should also be a zero. So conjugate pairs means that i's show up in pairs, and that the I term are opposites, okay, in those pairs. So the reason that you would get a plus or a minus is maybe you solved using the quadratic formula, or maybe you solved by doing the square root property. Those are both things where you end up with that plus or minus, right? So this is a good reminder. Don't forget the plus or minus when solving. Okay, so if you're solving using a square root property, or you're solving using the quadratic formula, make sure you have that plus or minus in there. Okay, so you get both answers. All right, so let me look at a few examples. I'm not going to do a ton because, like I said, the process itself is exactly the same as the last section. It's just we might get answers that have i's. So this one says the polynomial function f of x is given below has 1 as a 0. So if it has 1 as a 0, that means that x equals 1 is a 0. That also tells us one of our factors, right? If I move that 1 over, this means that x minus 1 is a factor of this polynomial function, right? And we want to find all the others. So this is kind of the easy case, right? If they give us a 0, we just go ahead and plug it in using synthetic. So I'm going to put the 0 that they gave me, which is 1, in my synthetic box and write out all of my coefficients. Excuse me, and here I'm not missing any numbers. So I have 1, -5, 9, and -5. I bring down my 1. 1 times the 1 in my box is 1. And we combine down and get -4. -4 times the 1 in my box is -4. I combine down and get 5. 5 times the 1 in my box is 5, and it does give me a 0. Yay, which we kind of knew, right? Because that one was totally given to us. So that's okay. Now that we have the 1 and we identified that it was in fact a 0, what we're looking at is this leftover piece to find all other zeros of this function, okay? So this is my remainder, this is my constant, this is my x, this is my x squared. So if I'm factoring this function, right, to find all the zeros, I know that one of my factors is x minus 1 because that was given, right? And my remaining factor is what I just got here from my synthetic division, my quotient here, which is x squared minus 4x plus 5. So just like we did on the last section, now we just need to factor or use quadratic formula to solve for the remaining zeros. So I'm going to go ahead and try sum product My sum here would be a -4, and my product would be a 5. I can get a -4 by using -5 and 1, but if I do -5 times 1, that's not giving me the +5. Okay, so in this case, this is not factorable. And if it's not factorable and it is a quadratic, right, equation, then the only other option we have is a quadratic formula. So we're going to go ahead and use x is equal to -b, so the opposite of my b, so the opposite of -4, plus or minus the square root of b squared, so -4 squared, minus 4 times my a, which is 1, times my c, which is 5, all over 2 times my a, which is 1. Okay, and then I'm just going to simplify. So I have a +4 plus or minus the square root of 16 when I square this, right? And then -4 times 1 times 5 gives me a -20 all over 2. I keep simplifying, which gives me 4 plus or minus the square root of -4 over 2. And then anytime I get a negative under the square root, remember that comes out as an I, okay? And once I pull that negative out, then I can do the square root of 4, which is just 2, right? So I get x is equal to 4 plus or minus the I that I brought out and the 2 that the square root of 4 simplified to. So I get plus or minus 2I all over 2. Now, because these are both divisible by 2, I'm going to go ahead and break this apart and write it as 4 over 2 plus or minus 2I over 2. That way I can just reduce each piece, right? So this gives me 2 plus or minus I. Okay. So those are the only remaining zeros that I have, right? Now, I am going to write this out the way that they do in this section. Now, on this one, I would just enter 2 plus I and 2 minus I. But on other problems, when you end up with complex answers, they have you enter your real zeros, the ones that turn into x-intercepts, separately than your complex zeros, because they have imaginary numbers, they don't become x-intercepts, right? So for just for instance, if I hadn't been given this, if I had found that on my own, so for instance, had I not been given this, let's say I found that on my own and I wanted to list all the zeros, my zeros would be 1 and it would be these two zeros, right? So I would write that as my real zeros, or my real number zeros. The only one I have is 1, right? The number 1, not 1 as a quantity. And then my complex zeros are the 2 that I just found by doing my quadratic formula. So it would be 2 plus I and 2 minus I. Now on an exam or on the final, I don't mind if you just list all the zeros together, but I wanted to write it like this just so that you're aware that Knewton will sometimes break those zeros up and list them as the real zeros and as the complex, okay? So the only time you list them as complex zeros is if they have I's, okay? Anything other than I zeros are real. Okay, so even if you have radicals, if you have the square root of 13, okay, that's still a real number 0. Okay, it's only complex if it has an I. All right, so this was our easy case, right? 1 0 was given to us. So let's look at some where the 0 is not given to us, and we have to go through the whole process of finding the potential zeros, plugging them in, yada, 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 right? Okay, wait for it. All right, so first example, find the real and complex zeros of the function. So here's our function. We're going to go ahead and look at all the potential rational zeros first. So we do plus or minus the factors of our constant term, right? So we're going to look at factors of 85 divided by the factors of our leading coefficient, which in this case is 1. And we love it when our leading coefficient is 1 because the only factors we have of 1 is 1, right? So basically, when we take any number and divide it by 1, we get that same number back. So our only potential zeros we have here are basically just the factors of 85. And the factors of 85 is 5 times 17. So it would just be 1, 5, 17, and 85 for our potential zeros. Okay, I'm going to go ahead and circle that. Okay, so these are the numbers we're going to start plugging in. We're going to plug in 1, -1, 5, -5, yada, 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 until we find one that works. Okay, so let's go ahead and start with, let's just start with 1. So I'm going to write out all of my leading coefficients, and notice here I'm not missing any terms. So I have 1, 13, 57, and 85. So I bring my 1 down. 1 times the 1 in my box is 1, which combines down to 14. 14 times the 1 in my box is 14, which combines down to 71. 71 times the 1 in my box is 71, and that is not going to give me 0. Nope. Okay, and notice what's happening. Since all of these are positive, if I just bring them down and multiply them by something, notice these numbers just got bigger and bigger and bigger. I didn't get any negatives. So if I don't get a negative here, you know, it's not going to be able to cancel out and give me a 0. So instead of trying a positive number, I'm going to try a negative number. And I think it's going to have to be bigger than -1. So let's try -5, because that's our next number on our potential list here, right? So 1, 13, 57, 85. So I bring down my 1. 1 times the -5 in my box is -5. 13 minus 5 is 8. 8 times the -5 in my box is -40. And 57 minus 40 gives me 17. 17 times the -5 in my box gives me -85. Yay! And we get a 0. Okay, so that means that x equals -5 is a 0, right? And if I were to move this over, that would give me x plus 5 as a factor. Okay, so I want to go ahead and factor this and just be able to write what it is that I have so far, right? So my function f of x is equal to this factor that I just found, x plus 5, times this remaining factor I have over here. So 0 is my remainder, so this is my constant term, my x term, and my x squared term. So that means I'm left with x squared plus 8x plus 17. Okay, so I want to go ahead and see if I can factor this. So I'm going to try sum product. My sum is 8. My product is 17. And the only thing that I can use to get 17 is 1 and 17. And 1 and 17 is not going to combine to give me an 8. So this one's not factorable. So I'm going to go ahead and use the quadratic formula on that second piece, right? And I'm not going to solve that one because we already have that one here. All right, so we have x is equal to -b, so -8 plus or minus the square root of b squared, so 8 squared, minus 4 times my a, which is 1, times my c, which is 17, all over 2 times my a, which is 1. And then I just want to simplify, right? So I have x is equal to -8 plus or minus the square root of 64 when I square 8. When I multiply 4 times 17, I'm going to get a -68 all over 2. So continue simplifying. I get the square root of -4 over 2. And again, I can bring this out as an I, right? So I get -8 plus or minus. Once I bring that I out, I can do the square root of 4 is just 2, right? So 2i all over 2. So last thing I want to do is just go ahead and write that 2 under each piece so that I can reduce it. Okay, so I have x is equal to -4, or sorry, here, let me write it out. -8 over 2 plus or minus 2i over 2, which is going to give me a -4 plus or minus I. Okay, so these are the two answers we got from using the quadratic formula on our quotient, and then we also got the -5 from our synthetic. So that means that our real 0 here, the only one we got was -5, and that the complex zeros that we got were -4 plus I and -4 minus I. Okay. Not too bad, right? Same process, just potentially having answers that have I's in them. All right, so I'm going to look at one more, and then y'all are going to have a couple to try, okay? So let's look at this next one. I guess if you were feeling really confident, you could pause the video and work this one. Just kidding. Okay, I'm going to go over it, right? All right, so we're going to find our potential zeros first. So when we find our potential zeros, we do plus or minus the factors of our constant term, which is -42, all over the factors of our leading coefficient, which is 1. So we have plus or minus all the things that go into 42 over 1, right? So basically just all the things that go into 42. And everything that goes into 42 would be 1, 2, 3, not 4, not 5, 6, right? 7. Okay, so 6 times 7 gives me 42, so now I'm pairing it up. So 6 and 7 gives me 42, so 3 and 14, and then 2 and 21, and 1 and 42. Okay, so these are all my potential zeros. So these are the numbers I'm going to start plugging in with synthetic until I find one that works. So I'm going to go ahead and try 1. And I'm going to write out all my coefficients. Notice it's already in descending order. I'm not missing any numbers. So 1, -14, 3, and -42. So I bring down my 1. 1 times the 1 in my box is 1, which gives me -13. -13 times 1 is -13, which gives me -10. -10 times 1 is -10, and that is not going to give me a 0. Nope. All right, let's try -1. So 1, -14, 3, -42. So I bring down my 1. 1 times the -1 in my box is -1, which gives me -15. -15 times the -1 gives me a +15, which is 18. And 18 times -1 is -18, and that is not working either. Boo. Okay, let's try 2. 1, -14, 3, -42. So we bring down our 1. 1 times the 2 in my box is 2, which gives me a -12. -12 times the 2 in my box is -24, which combines down to give me -21. -21 times the 2 in my box gives me a -42. Why is this not working? I feel like that should have been a 0. Look how close that is. Oh, I found the problem. Mrs. Williams had a typo. Go figure. Sorry. This should have been a +42. Okay, so let's see if that changes anything. If I go back and make this a +42, that's still not going to work. If I make this a +42, that's still not going to work. But if I make this one a +42, now I'm getting that 0. Yay! Okay, sorry. Mrs. Williams has typos sometimes. Glad that we caught it now before we plugged in all of these potential zeros and none of them worked, right? Okay, so this means that x equals 2 is a 0. Woohoo! And it means that x minus 2 is a factor. Yay! All right, so we can go ahead and factor this function a little bit. So this means that g of x is equal to this factor that we just found of x minus 2 times this factor that we're left with, our quotient down here. This is our constant term, this is our x, this is our x squared. So we're left with 1x squared minus 12x minus 21. Okay, and then I want to check to see if I can factor it, and if I can't factor it, we'll use quadratic formula. Okay, so my sum is -12, my product is -21. 21 I can get by 7 and 3, or 21 and 1. And neither one of those can combine to -12, right? So not factorable. So if it's not factorable, we're going to have to use a quadratic formula. So let's go ahead and do that. So x is equal to negative b. My b is already negative, so the opposite of a negative, plus or minus the square root of b squared, so negative 12 squared, minus 4 times my a, which is 1, times my c, which is negative 21, all over 2 times my a, which is 1. So we're getting so good at synthetic division, and we're getting so good at the quadratic formula. I told you these wouldn't go away. All right, so let's go ahead and simplify this and see what our remaining factors are. So, or our remaining zeros are. So we have a positive 12 plus or minus the square root. 12 squared is 144. When I multiply these next three numbers together, I have two negatives, so that's going to come out positive, which means that I'm probably not going to get an I answer, right? That comes out to a positive 84 all over 2. So 12 plus or minus the square root of 144 plus 84 is 228 over 2. 228 is not a perfect square, so let's see if we can break that down a little bit. So 228, well, I know it's divisible by 2, right? Because it's even. So that's 2 times 114. That's also even, so we should be able to divide that one by 2 and get 57. 57, is that prime? Let's see. Does 3 go into it? 3 goes into it, right? So this would be 3 times 19. Okay, so that's not going to help us. But we do have 2 copies of a 2, which means I can bring a 2 out, right? And I'm going to be left with a 3 and a 19, which gives me a 57 that's going to be left under that radical. So I have x is equal to, I'm bringing out the 2, so 12 plus or minus 2. And underneath I have 3 times 19, which means I have a 57 left all over 2. And then notice both of these are divisible by 2. So I can go ahead and write this separately. I can say 12 over 2 plus or minus 2 square root of 57 over 2 and just reduce each piece. So I have x is equal to 6 plus or minus the square root of 57. Okay. So notice we didn't end up with a negative under the radical, so we didn't have to pull out an I. And if we didn't have to pull out an I, we didn't end up with any complex zeros here. So all we have on this one is real zeros, right? And our real zeros are the 2 that we got from that synthetic, right? They gave us the 0 remainder. And then 6 plus the square root of 57 and 6 minus the square root of 57. There we go. All right, so on the next page, there are 2 for you to try. So I want you to go ahead and pause the video and work those 2 problems. If you get stuck or if you're ready to be checked, go ahead and unpause the video and we'll go over them. All right, so on the first one, notice this is one of the easy ones a little bit because they give you one of the zeros. So you don't have to find all the potential zeros here. You just take the 0 that they give you and plug it into your synthetic. Since you know that 3 is a 0, you know that x minus 3 is a factor. So you can rewrite the function as x minus 3 times whatever quotient you get left from your synthetic, which you should have gotten x squared plus 8x plus 20. And that's not factorable. So you're going to have to use the quadratic formula. Once you work out the quadratic formula, you should end up with a negative under your square root. So that comes out as an I. And once you simplify your answers, your 2 answers should be -4 plus 2i and -4 minus 2i. Okay, if you need to see that a little bit longer, go ahead and pause the video so that you can really work through that. Otherwise, I'm going to go ahead and move on to number 2. Okay, for number 2, you weren't given any of the actual zeros, so you had to come up with them yourself. Okay, so finding all the potential zeros, we do that by looking at the factors of our constant term, which here is 24, and dividing them by the factors of our leading coefficient, which is 1. So basically all the factors of 24, right, which we have written out here. Now, as you go through these, the first one, if you're going in order, the first one that you would get to work is a positive 2. Okay, that gives you a 0 remainder, which means that 2 is a 0 and that x minus 2 is a factor. So the quotient that we have left over here is x squared minus x minus 12. And this one is actually factorable. Hey, right? So if this one is factorable, we can use our shortcut. If you did the quadratic formula on this, you'll get the same answer. Okay, so this one factors into x minus 4 times x plus 3, which gives us the zeros 4 and negative 3. Okay, so we have the 2 that we got from this synthetic, and then the 4 and the negative 3 that we got from factoring or quadratic formula. So on this one, we didn't have any complex zeros. We only had real zeros, which were 2, 4, and negative 3. Okay? All right, so that is the end of complex zeros of polynomial functions. So you should now be able to do that section on your Alton Newton homework. If you have any questions, please let me know.